Well, it is now noon, and I don't want to eat into Bobby's time, so let me simply say it is my great pleasure today to introduce Bobby Gramacy, who's going to be talking about Gaussian processes and surrogates and such. I would like to mention that if you want to join the industrial statistics section of ISBA, you can do that without waiting until you have to renew your ISBA membership. And there should be instructions on our website, either now or very soon, on how to do that. So, Bobby's a professor at Virginia Tech, and he's written a great book on surrogate models. And Bobby, please take it away.
Thanks so much, David. Let me start by seeing if I can share my screen. Okay, I think that you can see my slides, but if you can't, I hope you will let me know, or if there's any other problem that needs my attention, or if you have any questions at any time, please don't hesitate to stop me. Thanks so much, David, for the introduction, for suggesting that we do this. I've been working on Gaussian processes for many applications, but in particular for surrogate modeling since I did my PhD at UC Santa Cruz back in the early 2000s. I graduated in 2005. So it's a rich area. I think there's still a lot of work that could be done. I'm excited about some of the recent developments in the community, but also in my own lab, and I hope to tell you about some of those at the end, but I want this to be primarily a tutorial. So I want to tell you about Gaussian processes. I think Gaussian processes are valuable in many areas. People use them in machine learning as general purpose learning machines. They use them in geostatistics, which is perhaps where they originated. And I use them in my field of surrogate modeling of computer simulation experiments. So I want to explain that to you a little bit, but then we're going to kind of change gears and go back to the basics of what a Gaussian process is. So a surrogate model is a model that you fit to a simulation campaign. So the data is coming from a computer experiment that's virtualizing some system. And you would do this whenever the actual experiment that you might want to do is too costly, because in this case, you would have to build an airplane in order to do the experiment, or impossible, like because you want to study how a spacesuit would work on an astronaut while they're on Mars. It's hard to do that without going to Mars, so you might virtualize it. Or unethical, a good example of that comes from epidemiology. If you want to entertain what might happen with a vaccination campaign or to study different drugs, you can't just make people sick and then give them medicines, but you can virtualize that environment. So by the end of the talk today, I'm going to tell you about a computer experiment that we used a surrogate model for that comes from aeronautics. So there's a simulation engine called SU2, which simulates the flow around an airfoil. And the simulations take about 1 core hour to run, depending on the input configuration. And the inputs that we're going to study have 4 shape parameters for a wing, and then environmental parameters like the angle and speed that the aircraft is flying at. And we're going to study an output that's the lift over drag ratio. So because the experiment is expensive in terms of time and energy, it makes sense to plan a limited campaign of runs, just the same way you would with an ordinary experiment, and then fit a model to the data that you get, to the input-output pairs of your computer experiment, and use your model to do something, to either make a prediction, or maybe solve an optimization problem, or to figure out which inputs are affecting the outputs. And just like with any statistical model, it's important to get accurate predictions, to get good uncertainty quantification. And in the context of computer simulations, it's important to be able to do that quickly, because if you can't do it quickly, then you could just run your computer model at more inputs instead of using the surrogate in lieu of that. So that's the surrogate modeling setup. Here's the overview of my talk. I'm going to back off from that and tell you what Gaussian processes are by describing the prior distribution and the posterior distribution that's involved. And then I'm going to tell you about my favorite application of Gaussian processes, which is to Bayesian optimization. After that overview, I'm going to tell you about some things that I see on the fringe or the frontier of recent methodology in Gaussian processes, handling large simulation campaigns, noisy and heteroscedastic outputs, calibration of computer models to field data. We don't usually have time for that, but I've got it in there just in case. And then I want to change to a really important area of non-stationary modeling fidelity, which will allow me to pivot back to that application that I just introduced to you, which ultimately ends up being about reliability in aircraft. Okay, so the first third of my talk is basics. I called it overview. So I'm going to tell you what a Gaussian process is. I'm going to start by showing you how to generate data, generate random functions from a Gaussian process with a little algorithm. So here we're thinking about functions. So I've got inputs and outputs. So I'll specify what inputs I want to use for my function, what x's. So maybe I make a grid from x1 up to xn. And then I'm going to build a covariance matrix in terms of the pairwise distances in those inputs. So my covariance matrix is e to the minus Euclidean distance squared between all pairs of the x's in my input set. And that covariance matrix will go in as the covariance matrix input to a multivariate random Gaussian number generator with a mean of 0. And I can draw any number of y's that I want from that multivariate distribution. So the code that's in the middle of the slide is my implementation in R of that three-step algorithm. It takes a little more than 3 lines of code to get it to go, but basically I've made a grid of size 100 in the input x space. I've calculated pairwise distances with a distance function, and I've exponentiated them, and then I put that matrix sigma into the RNV norm command that gives me multivariate normal random draws, and in fact I've asked for 3 of them in my code. We won't go line by line through every code block, but I just want to emphasize here that this presentation is authored in Quarto, which is the next generation of R Markdown. So what you see is what you get. Mostly the code there is to give you that comforting feeling, but also to show you that it doesn't take very much code to implement many of the ideas. And there are some cases later where we do some bigger experiments that I don't show you all the code, but I'll indicate when that's the case. So I've generated some y's that have a mean of 0 under a multivariate normal distribution, and a covariance matrix formed as e to the minus Euclidean distance. And then I'm going to plot those 3 sets of y's for you in the xy plane. So each one of these curves is one of the random draws that I got from that multivariate normal distribution. And you can see that they're kind of wiggly. They look like functions. They're functions that change direction a few times. It's not easy to predict which way they would go as a function of x in any particular realization. But because they come from a Gaussian distribution, there are some things that you can predict, like you know that you won't get very many functions going outside of the range of -2 to 2, because we all know that 95% of the realizations from a Gaussian with a unit variance will be within -2 to 2. All right, so that's how you generate random functions with a Gaussian distribution. We'll call that the prior distribution. Now I want to do some conditioning. I want to form a posterior distribution. So in order to build that up, I need to tell you about a fact of conditional distributions of Gaussians. And you probably know this fact already. In fact, I cribbed this fact from Wikipedia. So if you were to click on that blue Wikipedia link, it would take you to these identical equations with one difference. On Wikipedia, the random variable is notated as x, but here I've notated it as y, because what I'm going to be interested in doing is training with some data, some y's at my x's, and then I want to know the conditional distribution of my testing y's giving my training y's. So I've notated things here as y, whereas on Wikipedia, they use the letter x. So the result that we're going to use is about conditional distributions. And it says that if you have a multivariate normal random vector y that you partition into 2 groups, y1 and y2, then you can derive the conditional distribution of one group's given the other. And it doesn't matter which way around you do it. but here I've given you what you get for y1 given y2. So it's also multivariate normal with the dimension equal to the dimension of y1. And the mean of that multivariate normal distribution is a kind of projection, a linear projection. And the covariance is reduced compared to the marginal distribution of y1. So you learn something when you condition on y2. You learn something about y1. So these are some nice closed form calculations for multivariate Gaussian distributions. There are many others for Gaussians. We know that marginals of Gaussian multivariate normals are Gaussian. We know things about convolutions. We know all sorts of facts. Gaussian process regression uses this particular fact about conditional distributions. And what I want to do with that is I want to develop a predictor. Although you could call this the posterior distribution if you want, I want to make a prediction of y at new x's given some training data comprised of xy values. So I don't just want to generate random functions. I want to understand the distribution of random functions that explain my data. I want to solve the inverse problem, which is what Bayesian learning is all about. So here I'm going to use that multivariate normal identity for conditional distributions to develop the conditional distribution of some testing y values at squiggly x, given training x and y values that I've encapsulated in this variable dn. So it's my training data. So I'm getting a prediction given my training data. And the way that I derive that is through this linear projection of the training y values onto the testing x locations in y space. And I can get a mean vector and covariance matrix for any collection of testing calligraphy x locations that I want. So this result is just an application of multivariate normal conditioning. Sometimes these are called the Kriging equations, after a statistician who used to work in the mining community called Krieg. So this is sometimes what you'll see it referred to as in spatial statistics. And it has all sorts of nice properties. One of them is that it's the best linear unbiased predictor. But I'm not going to list all the properties for you. What I'd rather do is show you how it works on a toy problem. So here is a toy problem where I'm going to observe sine of x at 8 equally spaced locations within one period of the sine function. Was there a question? Oh, I'm sorry. Maybe I'm hearing somebody who's unmuted. I'm not sure. But please don't hesitate to interrupt me if you have a question. All right, so my training data are 8 examples of sine of x. My testing locations are going to be a grid of 100 locations within one period of the sinusoid where I want to make a prediction. So I need to calculate pairwise distances in my training data, and I need to calculate pairwise distances in my testing data. And then the most important part are the distances between the training and testing locations, because that's where that conditioning is really emphasized. So now I can follow those Wikipedia equations. I've got 3 lines of code at the top. The first one is just to invert my covariance matrix, and the other 2 are that linear projection, and then the quadratic form for the variance. And then I have a mean vector and covariance matrix for my testing locations. And then I can do a bunch of different stuff with that. I can draw example functions from that conditional distribution, or I can plot the mean of those functions for you, or as I'm doing here at the bottom, I'm extracting error bars through quantiles of a Gaussian distribution so I can visualize the function for you in a few different ways. So here is the outcome of this posterior predictive distribution. So the black dots are my 8 examples of sine of x. The blue line is the true function, which goes right through those black points. The black line is my mean vector on the testing grid. And you can see that that's very close to the truth for most of the input domain. Each one of the gray lines is one random draw from the testing multivariate normal distribution. So each one of those explains the training data locations. And the red dashed lines are my error bars. So my quantile-based uncertainty region plotted as a function of my inputs x. The first time I saw a picture like this, I was kind of blown away because I had learned a lot about splines and a lot about other numerical analysis, curve fitting techniques. And for my taste, maybe because I'm a statistician and I understand a lot about Gaussian distributions, or at least I thought I did, this was the simplest of all the different methods that I had seen. All I've got to do is calculate distances and then make linear projections and stick those into a Gaussian distribution. So I found that really tidy, and it gives a very nice prediction with good uncertainty quantification and other nice properties. Some people talk about the sausage shape of the predictive distribution, and I think you can see why when you look at this picture. North Americans sometimes refer to the football shape of the intervals, but I don't want that to confuse you if your footballs are rounder than our footballs are in North America. So I'll try to say the sausage shape throughout because I think that that's more universal. So that's the basic idea of Gaussian process regression. There are many ways to embellish it by customizing the covariance matrix and the mean function involved in the Gaussian distribution. I'm not going to make any changes to the mean in this presentation. I'm going to use a mean of 0 throughout, but I am going to embellish a little bit the covariance structure to introduce some tunable quantities. You could call those hyperparameters or parameters, if you will. One of them is called tau squared, that is in front of an identity matrix in the covariance structure. So it allows me to estimate a white noise process, or it allows me to smooth noisy data. And I am going to introduce what I'll call length scale parameters, theta, that allow the rate of decay of correlation to differentiate in each input coordinate instead of having radial dynamics as you would have with an ordinary Euclidean distance. And then I'm going to introduce a parameter called nu that scales the covariance matrix and allows me to have functions that differ in amplitude. Just like with any parameters in a statistical model, you have a lot of choice when it comes to estimating unknown quantities. Maybe as Bayesians, we would sample from the posterior distribution. I'm actually not going to do that in this talk. I'm going to leave all the Bayesian action in the conditioning of the multivariate normal. And for these other fine-tuning parameters, I'm just going to maximize the likelihood because that is a little bit tidier for a live Quarto presentation. So here's the log likelihood in the middle of the slide, which is the log of the PDF of a Gaussian distribution. And I can differentiate that with respect to my scale parameter, for example, set that equal to 0 and solve and get a closed form maximum likelihood estimator. Or if I give it an inverse gamma prior, I would get a conjugate update giving me an inverse gamma posterior. I have that in my book, but it's not here in these slides. You can then concentrate that parameter out, or you can integrate it out if you're doing a fully Bayesian approach and get an integrated likelihood. And then you can do the same thing for your other hyperparameters. It's a little bit more challenging. Maximum likelihood estimates are not going to be available in closed form. And if you're doing Bayesian updating, you're going to have to do some kind of metropolis scheme. Here I'm showing you how to use the chain rule for derivatives so that you can use an efficient numerical optimization scheme, which is what I've coded up on the next slide. So I've coded up here the negative log likelihood for my hyperparameters and its gradient. I'm not going to take you through this code. I think the point of this code is that it takes about 20 or 25 lines of our code to code this up, and it's all you need in order to learn the hyperparameters to a customized covariance function for a Gaussian process. And to demonstrate that for you, I'm going to do another example. So here I'm going to do a two-dimensional regression problem where my y's are a function of a two-dimensional x with some noise. So I'm observing this data with noise, whereas in my previous example, the sine function was not noisy. I'm going to put the negative log likelihood and its gradient into the optim function in R to optimize. I'm going to minimize the negative log likelihood to get my MLE. And it comes back with the 3 numbers that you need to dial those parameters into in order to maximize the likelihood. The value of those parameters are not super interesting to the human eye, which is, I think, why people call them hyperparameters, but you can think of them as sort of the best ones for doing the prediction, which is where all the magic of a Gaussian process is. So then I'm going to take those parameters and use them in my prediction equations by calculating my distances with those parameters and building the covariance matrix with those parameters and doing the linear conditioning and the quadratic form of the predictive variance with those parameters. And once I do that, I can visualize the mean surface and the variance or standard deviation surface, which is what I'm doing on this slide. So this is the surface that I learned from, I think it was 40 examples of X and Y. They were noisy examples. This is what I predict. This is my predictive mean function on the left, shown as a perspective. And on the right, I have a heat plot where red is cold or small and yellow is hot or high. And you can see that my predictive standard deviation is low where my training data is. So the training data are the open circles there. So this is the sausage shape manifest as an image plot for a 2-dimensional input space. So my uncertainty is lower where my training data is, and it's higher away from where my training data is. So I've given you a 1D example and a 2D example. There's really no limitation, at least algorithmically, in input dimension. All you have to do is be able to calculate distances and build a likelihood and its gradient from those distances. And in fact, the likelihood and gradient that I gave you before is agnostic to the dimension. All I have to do is plug in the x's and it'll give me the values of the likelihood and its gradient. So I'll be able to apply this straight away for a much higher dimensional problem. This example that I'm going to show you now is going to be in 5D, although you can do it in other dimensions. It comes from the Friedman function. So this is a function made up by Jerry Friedman for his Mars paper. It's a nonlinear function of a 5-dimensional input where there's an interaction between x1 and x2 and a sinusoid involved. There's a quadratic term. There are 2 linear terms. I'm observing this function with some noise. I'm going to train on 200 uniformly random in the input space examples, and then I'm going to make a test or predict for you on 1,000 random input locations. And then I'm going to make a little comparison in terms of accuracy. So we could use the code that I've already given you. I could use that optim function and put the negative log likelihood and its gradient in with these new x and y variables from the Friedman function. Or this allows me to pivot here to a library that does more or less the same thing. And there are a lot of libraries out there, but I know how to use my code the best. So I'm illustrating a package that I wrote called LAGP, and I intend to tell you a little bit more about why it's called LAGP later. But for right now, I'm using it just to do ordinary Gaussian process regression, just like I've told you about. It'll dial in those hyperparameters for you, which is that bunch of numbers in the middle. And they're very similar to the ones that you would get if you did it by hand. There are some slight differences between the package and what we coded up by hand. And then when you make predictions, the predictions are good. In this case, I'm comparing to the Mars algorithm, which I haven't reviewed for you, but this was the method that Jerry Friedman invented the Friedman data in order to illustrate. But you can see here, at least in terms of root mean squared error, the prediction that we get from the Gaussian process is better. It gives a lower RMSE compared to what the Mars algorithm does on this testing data. All right, so that's the overview. I think, if you understood that, and it would be great if you did, because I did it really quickly, but if you understood that, you would understand, I'd say 85% of Gaussian process regression. There are some variations, and you can, of course, make things more complicated, but that's the gist of it. And now I want to tell you about my favorite thing that you can do with a Gaussian process, and that's design an experiment sequentially, or what the machine learning community calls active learning. So active learning is this idea that you fit the model, maybe based on a limited initial campaign of computer model runs or of data, and then you ask the model, where would you like more training data? And you can base that on any aspect of the model fit. But in Gaussian processes, almost always the predictive distribution is involved. And you use a criteria based on the predictive distribution to make a selection and use that selection to augment your data and repeat, trying to create a virtuous cycle between data acquisition and learning. So the acquisition criteria could be anything. You could try to minimize the variance or minimize the future variance. Or what I want to tell you about is Bayesian optimization. So this is a scenario where the thing that you want to learn about is where your unknown function is minimized. So I want to know where x star is, which is the value of x that minimizes my function f, but I only get to learn about my function f through a limited campaign of evaluations. So it's kind of a classic optimization setup. But my function could be a noisy function. In this example, I'm not going to do the noisy function. I'll do deterministic. I assume that it's very expensive to evaluate the function, which is different than many classic optimization algorithms. So a tacit constraint on the solving mechanism is that it minimized the number of experimental trials, the number of evaluations of the function. And when I do a campaign of evaluations, I can fit a Gaussian process to it, which will summarize my prediction and uncertainty about that function. And I can use it to develop an acquisition criteria for active learning. And there are many of those in the Bayesian optimization literature, but the one that I think is the most common is called expected improvement. Expected improvement is measuring the amount by which your surrogate predicts that the function might be below the current best minimum. So they develop a random variable called improvement, measuring the amount by which a prediction, the predictive distribution of y, is below the current minimum, which I've notated as f-min, but f-min is just the smallest of the observations that you've seen so far. And you can take the integral of that improvement with respect to the Gaussian distribution of y that you get from your predictive equations, and that integral can be done in closed form. So you're taking an expectation with that integral, and they call that criteria expected improvement. And it has this formula on the slides that combines the minimum that you have so far, and it combines your predictive mean, and it combines your predictive standard deviation through this formula. This formula is kind of neat because it has two parts. It's separated in the middle by a plus sign, and on the left side of the plus sign is something to do with the mean. You want means to be low when you're minimizing the function. And on the right side of the plus is a standard deviation. Standard deviations are high when you have a lot of uncertainty, so it's worth exploring in that part of the input space. So people say it balances exploitation, small means on the left of the plus, with exploration, large standard deviations on the right of the plus. Let me show that to you in an example. So here's a kind of toy data set of 5 xy pairs. So let's say I've evaluated my function at these 5 x locations. And I've got the y's at those 5 locations now. I fit a Gaussian process to that data, and then I predict in the input space from that fit, and then I feed those predictive equations through an expected improvement function, which is like a lens that you use to look through the predictive distribution. You don't directly care about means and standard deviations. You care about how they combine to give you some kind of assessment of improvement about minimizing the function. So here's what this example looks like. I've got my 5 black dots, which are my training data, my Gaussian process prediction in black, and its uncertainty through error bars in dashed red. The best value I have so far, my F-min, is indicated by that horizontal green dashed line. And on the right, those 3 pieces of information are synthesized into expected improvement. So I have high expected improvement near x equals 2, because that's where I predict that my function minimum is. And I have high expected improvement near x equals 8, because that's where my uncertainty is high. And if I were to use this criteria to select a point to evaluate next, I'd probably pick a point near 2, because that's where my expected improvement is maximized. And when I do that, if that squashes down my expected improvement near 2, and so my next acquisition will probably be near 8. And the idea is that you would repeat that. I don't have any more slides on it. I just have that one. But the idea is that you turn that crank over and over again, making a recommendation based on your posterior analysis about where to train next to update your posterior so that you can locate the location of the minimum. Okay. So that's the first third of my talk, an overview of Gaussian process regression and my favorite application. There are many applications. I'll tell you about another application a little bit later that's sort of similar to that. Now I want to survey things that are on the frontier of modern research in Gaussian processes. So one thing that might be on your mind, because we're working with Gaussian distributions, is that I'm building a covariance matrix that is n by n, because I have n training data examples. So this is a potentially very big matrix. If n is big, I need to be able to store an order n squared times sized matrix. So that's big memory. And I need to be able to decompose it, because my linear projection involves the inverse, and the likelihood or the probability density function of a multivariate normal involves the inverse and the determinant. And the best way to do that with dense matrices anyway is with a Cholesky decomposition, which is a cubic time operation. So there's a lot of work recently on trying to circumvent this bottleneck. Cubic grows very quickly. If n is bigger than 1,000 or 10,000, this becomes prohibitively slow, limiting the sizes of the training data that you can fit with Gaussian processes. So a lot of the methods in the literature, and I've only got like 6 of them here, although there are probably 60 distinct ideas, so I wouldn't be able to fit them on a slide, but almost all of them involve inducing sparsity or low-rank structure or some kind of divide and conquer scheme in your, either in your covariance matrix directly or in the fitting enterprise. I'm going to tell you about the last 2 bullets just very briefly. One of them is a little bit indulgent because it's an area that I've worked on, and I think it's the simplest way to circumvent a cubic matrix bottleneck with Gaussian processes. So I'm going to tell you that that's the simplest way. The best way, I think, is the Vecchia approximation, the last one, and I'll tell you about that too. Okay, so the first idea, I call this local approximate Gaussian processes. So this is where the acronym LAGP comes from, which was the name of the software that we used earlier to fit an ordinary Gaussian process. And the idea is really simple. It focuses on prediction. So if I want to make a prediction at any testing point, little x, I could use all of my training data to form that prediction, but since my covariance structure is decaying quickly as a function of exponentiated inverse distance, I probably don't need all of that training data. It's probably sufficient to use only the nearby training data for the place where I'm trying to test or to predict. So the idea is to form a subset of the data of nearby locations. You could use nearest neighbors, or you could select a criteria that allows you to choose the most influential data subset. Both of those can be calculated very quickly even if your full training data set is large. For example, on this slide, I used a neighborhood of size 50, and I selected those 50 locations optimally, but it only took 0.041 seconds to do so. And then I can make a prediction, and it's very accurate. Its RMSE is to within 10 to the minus 5 of the truth. On the right, I'm showing you what one of those neighborhoods might look like if the full training data set is the gray dots. The gray dots are just showing you one little window of a big testing set. The testing set is actually of size 40,000. I'm showing you a subset of it. And if I use only the red numbered locations, up to 50 of them, that's what the optimally selected subset looks like in the input space. One thing that's good about this, besides it being simple to describe, is that it's embarrassingly parallel. You do one of these calculations for any location that you want to test, and since all of the calculations are statistically independent of one another, they can be implemented in a computationally independent way, and you can put it on separate cores of a multi-core workstation, or even separate cores of a GPU. In this example, I just did it on a workstation and made a prediction on a 10,000 sized grid with an 8-core machine. And it took less than a minute to do that. And I was able to draw the picture of my mean surface, which is what you can see on the right-hand side. So simple and parallelizable. But maybe an even better idea is that uses some similar operations, but is a little bit different, is what people are now calling the Vecchia approximation. So the Vecchia approximation is a sparsity-inducing method where you put zeros in the precision matrix of the multivariate normal distribution. But maybe an even simpler way to think about it is through the viewpoint of conditional probability and joint probability. So in the middle of the slide here, I have an identity that I think all of you know, which is that the joint distribution of y1, y2, and y3 can be factorized as a cascade of conditionals in any order you want. Here I've got the marginal for y1, and then y2 given y1, and then y3 given y2 and y1. So that is an identity. It's equal on both sides. And you can approximate that by dropping terms from the right-hand side of the conditioning bar. So here I dropped y1 from the conditional for y3. And when you drop one of those conditioning variables, it's like you're putting a 0. It's not like, you are putting a 0 in that coordinate of the covariance matrix if you were modeling these 3 y variables with a Gaussian distribution. Using this for Gaussian processes goes back to the late 80s, but it was recently rediscovered or let's just say modernized. It was modernized by 2 different teams of authors with slightly different perspectives on inference. So here's some of the details, if you will. So what we're going to do is we're going to take the likelihood, which is multivariate normal, and write that joint distribution as a cascade of conditionals and drop some of the terms on the right-hand side of those conditioning bars. Each one of those conditionals is a Gaussian distribution because it's an application of the Wikipedia result that I showed you earlier. So you could implement it that way. You could take all those conditionals and multiply them together. But it turns out that when you do that, you're actually working with a sparse Cholesky factor, and it's more implementationally efficient to work directly with that sparse Cholesky factor, which I'm notating as U on this slide. And this sparse Cholesky factor can be controlled to have at most m squared non-zero entries, where m is the maximum size of the conditioning set that you want to use. So think maybe 10 or 15 or 20, a small number. So even if you're dealing with 1 million training data locations, you can store this with 15 squared or 20 squared non-zero entries if you're using a sparse matrix library. To illustrate this for you, I'm using some code that comes from Matthias Katzfus, that fits these data very quickly using the Vecchia approximation. It takes 12 seconds to train the model using the data that I showed you earlier that had 40,000 training data locations and 10,000 testing data locations. So it's faster. It took LAGP 50 seconds, but this one is done in 11 seconds. And it's also more accurate. It gives a slightly better predictive accuracy. So that's scalability. Here's another thing that I think of as on the frontier, dealing with input-dependent variance. So if you have a nonlinear function that you're trying to learn that's nonlinear in its mean, it may also be nonlinear in its variance. This is a very common thing in stochastic simulation experiments, for example, ones that involve epidemiology and things like that. I've been working a lot with simulations that have input-dependent variance. The way that you do it is you put the variances under a Gaussian process prior the same way that you were putting the original functions under a Gaussian process prior. So really you have two Gaussian processes going on at once. They're linked together through the same training data, so they have a common likelihood. So I have two priors, a prior on the means and a prior on the variances. Both of them are distance related through Gaussian distributions, and I can perform inference for them in the same unified likelihood-based framework. And if you have concerns about giving variances Gaussian priors, you can do this with the log variances instead, and it works just as well. So here's the combined likelihood. It uses some notation that we haven't defined. I just wanted to show you that it had a kind of compact formula. And here is a library that fits one of these, what we call heteroscedastic Gaussian processes. So here is MLE HET-GP on the motorcycle accident data, which is a heteroscedastic simulation experiment. And this is what the training data and the fitted surface look like. On the left is the data and the surface, and on the right is what we learned about the variance function from the training data. All right, here are the slides I usually skip. This is on computer model calibration. There's a whole chapter on this in my book, but I'm looking at the time, and I want to get to a cooler thing, I think. So here is the cooler thing. It's common that training data coming from computer experiments or from spatial modeling or from machine learning have regime-changing behavior. So this means that they behave differently in some parts of the input space than others. So here is an example function that my student Annie Booth came up with to illustrate the challenge in using Gaussian processes or any other method when you have regime-changing behavior. So I'm going to skip the code on this slide and just show you the visual. So here's the function. On the left, between x equals 0 and x equals 0.5, it's wiggly and high amplitude. And on the right, say after about 0.5 or 0.6 or so, it's a linear function. So these are two different regimes, a very smooth is the wrong word because it's a calculus word, a very non-wiggly and a wiggly part of the response surface. Gaussian processes are not good at this out of the box or the way that I've described them to you because the only thing they care about is distance. They don't care about position. So if I'm going to learn a covariance matrix, it's going to be the same everywhere. All that's going to matter is the displacement between the pairs of inputs, not the actual location in the input space where their data are observed. This is something that people have worked on for a while. Again, I've got like 5 or 6 citations here, but there are probably 50 or 60 or maybe even more that could easily be listed. What we need is a non-stationary Gaussian process. Stationarity means that displacement is the only modeling quantity. Non-stationary means we take some position information in addition to displacement. The last citation here on this page where it says deep Gaussian processes, this is what I want to tell you about because I'm very excited about it. It's actually an old idea that goes back to Alexandra Schmidt, Antonio Hagen, in 2003, but they didn't call it deep Gaussian processes because we didn't have deep stuff at that time. We were still pretty shallow, but the machine learning community has latched on to the idea of deep neural network modeling and transferred some of those ideas over to Gaussian processes. So that's the last thing that I want to tell you about here before I wrap up. It's this Annie Sauer's PhD dissertation work on deep Gaussian processes and a cool example in reliability that allows me to connect back to that airfoil example from the beginning of the talk. Oops, I skipped 2 slides on accident. So here we are. What is a deep Gaussian process? A deep Gaussian process is a chaining together of ordinary Gaussian processes in the same way that a deep neural network is a chaining together of neural networks. So here's a nice figure that Annie made that I think gets the point across. What I've told you about so far in this talk is a typical or shallow Gaussian process illustrated by the left panel of this diagram. So I have outputs y, which is y1 in this panel, as a function of inputs x. And I can get those y's by drawing from a multivariate normal with a covariance structure formed from inverse distances in x. Well, now if I take those y's and I make them inputs to another Gaussian process, this is the sort of smaller latent Gaussian process figure between the first and the middle panel. So I'm sticking those y1s as inputs into another Gaussian process and generating a second set of y's, y2, with those inputs, which are linked to the original inputs x through the y1 value. And then in the middle panel, I'm plotting for you just the y2s as a function of the original x's. But I'm showing you the effect of y1 with the color strip at the bottom. So you can see that the middle of the x's, the strips are more spaced out, and at the edges, they're more compressed because the y1 function has higher slope for middle x values and shallower slope or flatter responses at the edges. So it's like we're stretching and compressing the original inputs x through this y1 variable. And even if both Gaussian processes are just functions of distance, by doing this stretching and compressing, we're taking the original inputs into account. And you can do this as many times as you want. We have an additional layer on the right, a 3-layer Gaussian process. You can do this 4 times or 5 times. We found in our own work that you don't need to do this very many times. In fact, all of our best examples have just a 2-layer deep Gaussian process. So what do we have mathematically? We have a hierarchical model with, we're changing the labels of the variables here. I'm not using y1, y2, and y3 anymore. I've just got my y's as a function of x's through a latent warping variable w, which is potentially multiple warpings of a p-dimensional input space. There are many ways to do this, but the idea is that I've created a latent variable w that has a Gaussian process prior that relates my original inputs x to my responses y through inverse distances. And how do I infer this unknown quantity? Well, I have all of the choices that I would normally have for inference. I could use the likelihood, I could use cross-validation. We're going to take a Bayesian approach and try to integrate over the posterior distribution of the warpings. We do this with elliptical slice sampling, and there are details in Annie's paper. Other people from the machine learning community have preferred variational inference, which is a Bayesian, but ultimately maximization-based method. And we found that for the problems that we study, this is both slow and compromises uncertainty quantification. So here's what a deep Gaussian process fit looks like on that data. And you can see that it does a good job of getting the uncertainty quantification right. It knows that the right-hand part of the input space is easier than the left part of the input space. And the way that it's able to get those narrower error bars on the right is by flattening out the warping of the inputs on the right-hand side of the space in X space. So that's being shown in the second plot on the right, my warping variable. You can see that's higher slope for low X values and shallower slope for higher X values. Each one of those gray lines is one sample from the posterior distribution through elliptical slice sampling of this latent W variable. You can see that there are some identifiability issues. It could start low and then go high, or start high and then go low. But all that matters to the Gaussian process is distances. So the positions of those don't matter at all. And the likelihood doesn't have a preference over one of the other. Here's a quick 2D example showing you how we warp two X coordinates in this G function example into two W coordinates sampled with elliptical slice sampling in the middle two panels. And on the right is a kind of map showing the original X's in black to their W coordinates in red. So we've got a two-dimensional warping variable for this example. We did a 4D version in a kind of bake-off where we pitted a deep Gaussian process with elliptical slice sampling against the Gaussian process that I introduced earlier in the slides. And you can see that the deep one on this problem is more accurate. It has lower RMSEs at each training data size, and it has better uncertainty quantification measured through a scoring rule, where in both cases lower is better, shown on the right-hand side. We were able to fit reasonably big training data sets in this example because Annie worked out how to apply the Vecchia approximation in this deep Gaussian process modeling context. We've been able to fit training data sets with these deep Gaussian processes as big as 100,000 training data points in a reasonable amount of time. All right, so I want to turn now back to the airfoil example that I opened the presentation with. We fit a training data set of size 500 sampled in a space-filling way throughout the 7-dimensional input space. And we fit 3 different models to that training data. And then we tested on 4,500 uniformly spaced inputs and measured root mean squared error and the score on those testing data. And you can see that by RMSE and by score, the deep Gaussian process is the winner. So this data benefits from the accurate prediction that a deep Gaussian process can provide through the warping of the input variables. And also you can see that variational inference is sort of disappointing for this problem. I'm not really sure why that is, but we have not had good luck with the code that the machine learning community has provided for deep Gaussian processes by variational inference. But it could be the style of examples, the computer experiments that we're training them on, because I know they get good results in some other image classification contexts. All right, well, suppose that we weren't just interested in getting the most accurate predictions. Suppose we wanted to identify the parts of the input space that could be labeled as passes or failures, which you can imagine is really important for building airplanes. You have safe and unsafe, or efficient and inefficient operating conditions. And if that's the thing that's most important to you, then you might be able to target that modeling goal and do better than you would do if you just developed a design without taking that into consideration. So here I'm showing you sensitivity and specificity to predicting whether the lift-over drag ratio is bigger than 3, which is a pass, or less than 3, which is a failure. And you can see that the deep Gaussian processes, again, win at this method, at this goal compared to an ordinary Gaussian process or variational inference. But it's interesting to ask, can you do even better if you learn from the data with this goal in mind? So the way that we do that, this is kind of like a Bayesian optimization, except instead of trying to optimize, what I want to learn about is the classification threshold of being above or below that safe lift over drag operating condition. So I'm creating a classification problem from a regression problem, and I can learn about the probabilities of being in one of those two regimes through a Gaussian distribution. I get predictions from my Gaussian, and I use the CDF to convert that into a probability of being in one class or another. And then I can use entropy as a measure of my uncertainty about those classification probabilities. Entropy is a function that's maximized when the probability is at a half, which is what is being illustrated by the panel on the right-hand side. So to illustrate this in a Gaussian process context, here is a simple two-dimensional function that we call the plateau function. It's actually a two-dimensional CDF calculation. And if we train at 5 input pairs represented by the open circles, then we can get a prediction surface that's on the left, and then a standard deviation surface for that prediction that's in the middle. And if we were trying to learn about the level set where the response is 0, which is indicated by the blue line on the left, we could try to use the mean and standard deviation information. And a good way to use that information is through the lens of entropy. So entropy combines the mean and the standard deviation to give you one quantity, which you can see is high in yellow or white, where the blue line is, which is where we're trying to find to separate these two parts of the input space. So we want to be able to use entropy to develop an acquisition criteria to select new points. And you can see that if you were going to do that, you would put a new point near x1 equals 0.6 and x2 equals 0.2 or something like that. The trouble is it's hard to operationalize this because the entropy surface is 0 in a lot of the input space. All of the red area that's far from the yellow area is numerically 0. So it's hard to navigate gradients in a part of the input space, which is basically 0. And entropy also has this myopic property that it tends to not spread out enough points when you choose it as an acquisition criteria. Annie, in her dissertation, developed a process for solving both things at once, but I'm not going to take you through it because I can see I only have a couple minutes left. I'm just going to show you the results that we got with it. And you can see that as we increase our training budget size from 20 to start out with to 150 at the end, that our method, which is the green line, is giving the best sensitivity results with the smallest budget that's being made available to it. We made a comparison to other methods who were also doing active learning, but we were able to be more efficient than those, and we compared to static training data sizes, and we were able to compare favorably to those. This is on that plateau function I just showed you, but in 5 dimensions. When we go back to the airfoil example, we weren't able to do as many repeats because the simulator was expensive to run, but we found that all of our optimally acquired through entropy runs were able to give us better sensitivity and specificity than any of the static ones that we did without active learning. So if you're interested, you can read more about that in Annie's paper from 2023. So that's what I wanted to tell you about. Thanks so much for listening. I'm going to leave you with this. So if you want to learn more about the deep Gaussian process examples, you can read our papers, and all of the code behind all of those papers and the code for this talk involving those examples comes from our Git repository. And everything else, all the basic stuff in the first 2/3 of the talk is covered in my book. And the book is available for free on my webpage if you want it. If you need a paper copy, you have to pay CRC for that. But if you just want to read it on your screen, you can read it for free. So thanks very much for listening. It's a thrill to be here and talk to you. Thanks again, David, for setting this up.
Thank you, Bobby. That was lovely. And yes, I have a hard copy of your book.
All right, well done.
So let's open it up and see if anybody has any questions. Maybe you should stop sharing your your screen, Bobby.
Yeah, I can do that.
Thank you, Kapil. Does anybody have any questions or comments?
I see one in the chat.
Good for you, McKenna.
I see. What did you say, David?
McKelly was holding up his copy of your book, Bobby.
Oh, well done, Mikhail. I didn't see it. Yeah, I wasn't looking at it. Thank you.
Well, if nobody's going to ask a question, I shall. Let me jump back to your Wikipedia leading example. When you calculate the conditional distribution given an observation, you're assuming that sigma is known. Suppose instead of a known sigma, I have a joint multivariate Gaussian inverse Wishart independent distribution over the mean and the covariance matrix. What would the conditional look like in that case?
That's a terrific question, David. I don't know is the short answer. A slightly more thoughtful answer is that people have tried to be more non-parametric about the covariance structure, and there has been some limited success with that. And it involves some of the things that will be familiar to Bayesians who work with covariance matrices on graphs and stuff like that. But I don't think that they've been successful enough to dethrone some of the distance-based methods that I showed you about, perhaps with some more embellishments to make things a little bit more flexible.
Thank you. Does anybody else have a question or a comment?
Hey, this is Charlie.
Hi.
Just to answer your question, is that multivariate T if you do the inverse Wishart on the covariance? I mean, at least the unconditional version, we know that's just multivariate T.
Thank you. That's probably right.
I think you're right.
Yeah,
In fact, if you, I'm not sharing my screen anymore, but we have a parameter that governs the scale of the covariance matrix. And if you sample that from an inverse gamma conditional distribution, then your predictive is already multivariate T. I didn't take that, but even in its simplest form, it's multivariate T.
Yeah, so that might actually, implementation-wise, probably is still pretty straightforward. I mean, so it's probably worthwhile trying it. Might have some additional benefit. Yeah. Now, there's one problem with multivariate T though, which is T is for the robustness, but the problem is that it's the same degree freedom, control all directions. That actually is a big problem. I think people have tried to create a multivariate T-like distribution, but it would allow different degree freedom in different tails. But the problem when you do that, you will go outside the ellipsoid kind of a construction, and so that has been a challenging problem. So maybe a deep T, I don't know. Like you iterate the T in the different. Well, deep T is good. I would love to have deep one, but deep T is good too. So maybe go different directions. Maybe able to solve this problem. Maybe one iteration never solved the direction problem, but maybe we iterate, we couldn't solve problem. That actually could be quite interesting.
Definitely.
There is a question in the chat from Zhongyang Huang. Any thoughts or comments on why Vecchia approximation works well or better?
The difference between the Vecchia approximation and the local one that I showed you about, the biggest difference is that the Vecchia version is a global model. It's still using all of the training data, even though you've introduced some conditional independence. Whereas the local approach is really throwing data away, which is inefficient. So it's a simpler method because it's super easy to describe and implement, but it is not using all of the data.
Jordan has a question or a comment.
Yeah, thank you. So does it seem like the improvement over kind of standard GP of a deep GP, is that kind of like a Gauss Markov? Is it the reason that you're doing some, you're kind of like, you're trying to model the covariance more realistically, like not using the stationary assumption, and instead of toggling like a parameter within the parameterization of the covariance matrix, you're moving the x's. So sort of like, I don't know, like you're shrinking a little bit towards stationarity, but you're getting the benefits of this variance reduction because you've gotten a little more towards whatever the real covariance structure is. Is that how you maybe understand it? Or?
Yeah, and I might rephrase it in the following way. I think most functions, whether they come from computer models or from real data generating mechanisms, are not stationary. So that means that if you have enough data from them and you try to fit them with a stationary model like an ordinary Gaussian process, it's going to be inefficient. And that if you use a Gaussian process instead, deep Gaussian process instead, that it could potentially do better. However, deep Gaussian processes introduce a lot more flexibility. So if you don't adequately regularize them, they can go all over the place and you can get all sorts of unstable predictions. So I think it's the standard estimation risk scenario where you want to make things more flexible because you think in most cases you need that additional flexibility. But if your data is not strongly non-stationary and if you don't have a lot of it to reveal that non-stationarity,
Right.
then you risk getting an unstable prediction.
Yeah. Okay, cool. Yeah, that's super interesting. Thank you.
Jolly?
Just to follow up on the question about the Vecchia's approximation, does it actually depend on the ordering? Because if you do this approximations, how do you deal with that?
Does depend on the ordering. There's a whole lot of literature about what the right ordering is and how to form your conditioning sets with that ordering. People have used design techniques in order to choose those things. And in some situations, making what seem like optimal choices helps. However, it's really hard to beat a random ordering and a nearest neighbor conditioning set.
I see. Is there a sense that when you go through the deep Gaussian that at the different layers you different ordering, randomize through that?
We have experimented a little bit with that and not come up with anything we liked better than random ordering. But I think
Just random ordering.
Yeah.
Thank you.
Any other questions? Oh, Richard, yes.
Hi. Can you hear me? Yeah, sorry, I was actually running on the treadmill while listening to your talk, so probably just being slightly out of breath. But my question is this: you were talking about a catastrophic failure situation, as I understood, with your aircraft wings. Such situations might not follow Gaussian distributions. Have you done any experimentation with non-Gaussian distributions, such as, for example, using extreme value distributions for excesses over a threshold or anything of that nature?
We have not. The closest I've come in any of my work, but not this deep Gaussian process work, is to use T distributions. But we have not used any of the things that you talk about. But I think that would be very important for that application.
Okay, thank you.
I actually have one minor question. Hi, Bobby.
Hi,
Great,
Ed.
great stuff. So when you're talking about the local approximation, the one right before the Vecchia, when you showed us the plot there, and I was surprised, I expected the plot to be more or less, sort of one circular region, but you had these diagonals going off where you had some points far away along diagonals. What was going on with that?
I'll try to share my screen again so people can see what you're talking about, and I can make sure that I'm thinking about the same thing that you are. Let's see, where is my... I'll just share the whole thing.
Okay, I bet we're talking about the same thing. Yeah.
Okay, so
yes.
you are talking about this one.
That one.
Yes.
That's
On
right.
the
So
bottom right.
you got it. It should have a large degree of symmetry to it, but
Right.
it doesn't in this instance because the training data is on a regular grid and the predictive distribution is the predictive location in green is
Right.
offset of that grid. So it's creating a kind of aliasing thing where you can't get exactly the training data locations you want. They've got to be on the grid, so they take on this weird shape.
Okay. Okay. Thank you. I mean, I thought it had something to do with the correlation structure, but I guess it's more being off the grid.
It is. It's a totally radial structure, and we've done some work to show if you can choose training data locations continuously anywhere you want, what those would look like. And they kind of create these spirals, actually. They're beautiful to look at. But when you're restricted to the grid, it's harder to interpret.
Okay. Thank you. Thank you very much.
Anybody else? If not, let us thank Bobby one more time. And it's great to see everybody here.
Thank you.